Hi guys, today I'd like to talk about parent function transformations. So we've looked at parent functions and we've seen that they are kind of the thing all of our equations fall into, right? So we looked at the linear parent function, right? F of x equals x. And it turns out its transformation function is what we think of this f of x equals mx plus b or y equals mx plus b, right? The difference being this first is just the parent function, and then every line we've seen is a transformation of that parent function. So a translation is what are we adding as far as a b value. So here we've got this f of x equals x minus 4, where b has now taken on the value of minus 4. What that graphically does is take this line that's the perfect diagonal, that's y equals x, and moving it down 4 points on the y-axis, right? So the top line in this graph is y equals x, and then y equals x minus 4. So having that minus 4 is move the entire line down 4 units. So this b value that we see at the end of f of x equals mx plus b, that b value is the thing that tells us that we move that graph up or down, right? It's the same graph of y equals x, but we're going to shift it up or down by how many ever units it indicates with that value of b. So we know that's our linear transformation, right? Mx plus b. It turns out that m value stretches or compresses our graph. So here if I put a 2 in front of it rather than the perfect diagonal line that we can see that goes from corner to corner, it makes my graph steeper. Right? It's stretched it out by a factor of 2, stretched it out vertically. A compression is when m is less than 1, right? So here I had 2x, and now on this one I'll have a quarter x. And it ends up, instead of stretching, it compresses. So when we talk about stretching and compression values, this is what happens on x, right? So if we have a value over 1, then it kind of makes our entire graph taller. Whereas if it's less than 1, like this 1/4 value, it compresses that value and it kind of makes the entire graph seem shorter. So m is a stretch or compress, right? So m is it going to be taller or shorter on the graph? And then b is moving it up and down. Reflection, just to kind of, whatever that value is in the front, that's going to reflect it over the x-axis, right? If we have negative x, that reflects over the x-axis. So this is the general form of all of the transformations of functions, right? This kind of gives us some different examples. But here we see every single a value is going to either cause it to stretch, to compress, or to reflect over the x-axis, right? So all of these a values, they either mean stretch the graph out, compress it, or to reflect it. If we have an h now, we've added a new value. We have an h in here. And notice that every single one of these h's is either in parentheses or it's part of the operator. Right here it's under the square root, it's inside the absolute value, or it's part of the denominator in our reciprocal or rational function. Whenever we have a value like this that's included in a parentheses or in the operator, that moves the entire function to the left or the right. And it's always the opposite. So if I have a minus h in here, that does not mean move it to the left negatively h. It's always going to be move it to the right. So if this is negative, you're going to move it positively. If it's positive, then you move it negatively. And then finally, k is like that b in y equals mx plus b. This moves our function up or down. So again, a is a stretch, compression, or reflection over the x-axis. The h value moves us left and right, and it's always the opposite of the sign. And then k moves our function up and down. Here I have this quadratic function, f of x equals x plus 2 squared. You can see the graph that is symmetric here to the x or the y-axis is the graph of y equals x squared. By having this plus 2, we need to take the base of that graph and shift it to the left too. Remember, it's always the opposite of this sign. So this says rather than the bottom of this graph being at 0, 0, it needs to be moved over and be at -2, 0. So if you look at the bottom of the graph that's shifted to the left, the base of it would be at -2, 0. We move it 2 units to the left. Similarly, if I've got x minus 4 squared, that's going to shift 4 units to the right. So here we see with the plus 2, we moved 2 units to the left. And with a minus 4, we moved 4 units to the right. So h, again, it always moves it left or right, and it's always included in the parentheses or in the operator. It's never out on its own at the end. That, remember, is a vertical translation. Here we can see if we have x squared minus 2, the graph that's at the top of this is x squared, and having this minus 2, see, it's not in parentheses. It's not in the operator. So here, this is a vertical translation. This would be a k value, right, of minus 2. And I always like to remember that when we have it outside, it's always telling you the correct thing to do, right, to subtract by 2. It's only when we're in parentheses or in the operator that it's the opposite logic. Right, so we had a vertical translation to move down 2 units there. And here, instead of having a minus 2, we've got plus 5. Well, that means we need to move it up 5 units, right? That's a translation of moving the entire graph up 5 units. So k moves us up or down. Let's look at another example here. Here looking at a values. So when you look at this graph, it shows you these two functions, and one of them will have its x values increased for the same y value. Excuse me, the same x values will cause it to be higher. So it's actually going to be this interior function is going to be 2x squared. And it's a stretch of a factor of 2, right? So if, say, for instance, if we plug in 1 into x squared, we would get 1 out, but here we would multiply it by 2. So this is going to grow taller 2 times faster. An example of a compression, here we've got 1/2 x, right? And so rather than making it taller like this interior function, here now 1/2 is this exterior part of the function, where when we compress it actually lays the entire function out and it opens it up. So it's kind of compressing those y values down, and we get this kind of opening of the parabola. Stretches kind of close that parabola, whereas compressions are going to open that up for us, right? Compress it by a factor of 1/2. And then let's look at what a reflection looks like, right? If we've got that negative out in front of x squared, that's going to take my entire graph and flip it over, right? Reflect it over the x-axis. Right? So A can either stretch, it can compress, or it can reflect. Now let's look at an example here with the square root function. If we notice this value of plus 5 is inside the square root, it is not outside, so this must be a horizontal translation. And here we can see the graph, right? The square root function is only defined up in the first quadrant. So this one that comes over here on the left and comes over to the right, that is my x squared plus 5, but recall if it's plus 5, that means shift it 5 to the left. So here we can see the whole graph has been shifted 5 to the left. And here with a minus 4, again, opposite logic, we want to shift our entire graph 4 units to the right. So if you have a plus inside that square root, that's moving it to the left. And if it's a minus, it's moving it to the right, which is kind of against our logic. We think adding should make it more positive, but that's not the way that this works out. It's always the opposite. So if it's plus, you move it to negative side, or more negative. If it's negative, it becomes more positive. So h, again, moves us left or right. Here we've got the square root function, but notice our value now is on the outside, right? It's not underneath that operator. So this is the square root of x plus 3 outside of that. This is going to be a vertical translation, right? We're just shifting our entire graph up 3 units, right? So just taking that parent function graph and shifting it up 3. Here we'll take our parent function of the square root of x and shift its entire graph down 8 units. And you can see here, right, that all it did is just take that same exact line and move it down 8 units. So K moves us up or down. Now let's go ahead and look at some examples of some stretches and compressions here. Now we can really kind of see the difference, right? So in this first example, we've got a stretch. And this taller line is the line that represents 2 times the square root of x, right? It's going to take every output value and double it. Whereas here on the second value, we're going to compress every value by 1/4 of the original, right? It's got a compression factor of 1/4. So this line that almost hugs the x-axis, that's the new compressed line. And then finally here we've got the square root of negative square root of x, or excuse me, f of x equals the negative square root of x. That negative out in the front, again, means a reflection over the x-axis. And this right here is actually some visual proof of why parabolas do not have inverse functions, unless you have a restricted domain. Because you see, this is what a parabola looks like on its side, and it does not pass a horizontal line test, so it's not a function. But we can think of this now, the bottom part of this kind of sideways parabola, that's the reflection of this top line. So if your parent function is x squared, here's your transformation function, a times x minus h squared plus k, where a is the compression, a stretch, or a reflection. H is a movement left or right, dependent on the symbol in here. We usually typically write this as minus h in this generic form, but this could be a plus or a minus in your actual equations. And then plus k, that is your vertical translation, shifting up or down. Right, so your horizontal translation could look like x plus 2 squared, right? That would be a horizontal translation, moving it 2 units to the left. And you can see here now if we've got a minus in there, we've got this, another horizontal translation moving 4 units to the right. And now let's look at a vertical translation, right? If we have that minus 2 out at the end, you can see that it just shifts the graph down 2. And if it's a plus 5, it shifts our whole graph up plus 5 units up. So again, these are our k values in this equation, a times x minus h squared plus k. K moves us up or down. And now let's look at those values when a takes on different values here for quadratics. We could have a stretch, right? Anything greater than 1 is going to be a stretch, increasing those y values. Compressions, again, remember, shrinks all the y values down and opens that parabola. And then a reflection is when we have negative x, and you see it just flips our entire parabola upside down. A reflection over the x-axis. Going through the square root function, here you can see we've got a times the square root of x minus h plus k. Remembering that h is our horizontal translations, right? Moving it left or right. And now let's go back and look once more at the vertical translations, right? These are our k values, where we either shift up or we shift down depending on what value we've added. Square root function, again, here we're looking at the stretch, the compression, and the reflection of that square root. Again, values over 1 give us a stretch, values less than 1 give us a compression, and if it's negative, then that can give us a reflection over the x-axis. And remember that you could have like a negative stretch value, right? So it's going to stretch the values out, but also flip everything over. Here's our absolute value function and its transformation function, right? A times the absolute value of x minus h plus k, where h is our horizontal translations, right? Moving 5 units to the right or 2 units to the left. H, again, is moving us right. And recalling that k, whatever this value is outside of it that's added or subtracted, is a vertical translation, moving the entire graph up 2 units or down 4 units in these specific cases. And let's look again at what those a values can do to our absolute value, right? We can have a stretch by multiplying by 2. We can compress because we are compressing by a factor of 1/4, right? Taking every value and making it a quarter of that value. Or we can reflect it across the x-axis. But recall here that this is outside of our absolute value. We do not put that negative inside it there. It's out in the front. So our cubic function, I'm going to go through these pretty quickly, but I just want to make sure we get a chance to look at what they all will look like, kind of. Here we've got x plus 2 moving 2 units to the left, or 4 units to the right. So again, h moves us left or right. So as we can see here, right, x cubed minus 3 shifts our entire graph down 3, plus 5 would move us up 5 units. So k is an up or down movement. And let's again take a look at those values that we have for a, right? We can have a stretch, which is going to stretch our entire graph out. We can have a compression, and we can have another reflection. This one makes kind of a cool reflection, right? The original graph would be the ascending parts, and the descendings would be that reflection over x. Here's our rational function. These ones do look a little bit different, right? We have a times 1 over x minus h plus k. Just recall that you can see that h is in the fraction, right? It's not outside of that. It's kind of it's always in that parentheses with the x. H is my horizontal translation, right? Moving that graph left or right. So as you can see here, 1 over x plus 2 would move the entire graph to the left 2 units. Or this next 1 over x minus 4 would move us 4 units to the right. And in these first problems, we're really going to be looking at identifying what the transformation was. Let's look at our vertical transformations, or translation, right? This is a rigid transformation. Right? If we have plus 3, that's just going to shift us up 3 units. Minus 5, again, now we notice that this value is not down there on the bottom of this fraction with x. It is outside. That's what makes us know it's vertical, right? Not horizontal. This is a movement up or down because this is that k value that is not included in the fraction. And we can again look at the stretch and the compression of these values here, right? Stretches and compressions. And you can have a reflection of this, right, negative 1 over x. And you can see it here. It's this, the bolder line is the function 1 over x, and the lighter line is this function negative 1 over x. And you get this kind of interesting squared shape here in the center. It almost looks like a star. And that's a reflection over the x-axis.